Lesson 72, Structural Design. We will discuss some choices in design with torque. Now, I actually think this lesson might be interesting for some of you. I bet there are some people sitting here thinking, you know what, I'm actually not interested in becoming an engineer or a physicist. I am interested in maybe some people, there's usually one person every 2 years or so that says, I want to be an architect. And I think this might be interesting because it's sort of interesting that what we're going to do is we're going to take the ideas that you may have learned from physics and sort of say, well, how would they apply to an architectural structure? Now, obviously, this is not a 101 structure and physics, but I wanted to give you guys maybe at least a basic sort of look and sort of to understand, well, this is why we care about these types of structures. This is how we think about them in a physics kind of concept. And of course, there would be a lot more stuff that we could do, but I thought we'd just, part of it is just to talk about one basic idea, but I'm going to add an extra idea to it because I thought it would be relevant. But before we do this, before we look at lesson 72, structural design, I want to go back to finish the other lesson and talk about what we were doing last lesson. By the way, ladies and gents, if I'm going too quickly, please say so in chat. I feel like I'm going rather fast today, but you know, you have to let me know. So let's go back to this here. We talked about net torque. Now, a net torque in an object is the overall torque. It can be found by adding up all of the component torques or the small torques together. We said that a clockwise one is positive, anti-clockwise is negative. Or if you remember all the way back, we said anti-clockwise is out of the page, clockwise is into the page, or in forwards. But we're not going to deal too much with that. I think we're mostly going to use positive and negative. Do you notice how I've mixed this up? Look, I've done a positive sign here and I've written the word negative here. Like we've done two different conventions. It's really bad writing. We did this quick example, and then what we did was we said, well, let's break this down into a simpler picture. And so instead of drawing these scales and all this stuff, we just thought, well, let's just do how far away from it is and what are those forces. And then we've got 5 newtons down and blah, blah, blah. We worked it out. We talked briefly about center of mass. Ultimately, center of mass is the center of the balance point of a piece of an object. It's the point where all of the mass is considered to be, and it's the point where there's just as much mass to the left and to the right. This will, for most substances with equal density in all directions, be in the middle of that substance. Obviously, for a hammer where there is different densities, it's not going to work. Then we looked at this question. We only got halfway through this question here. So my job is going to be today to wrap this question up. What we did last time, and let me just refresh our memories. I'm actually going to choose a different color. We're going to go with orange. What we did last time is we said, well, and I'm going to just, if you guys have got this question half written down in your books, then you might want to add to this question instead of putting it a whole new start here. But just for those of you that didn't know, a brief catch up, we said a young boy builds a bridge over a river and laying down a piece of wood. The wood weighs 40 kilograms. And so what we did is we said if the wood weighs 40 kilograms, we said F equals mg. We said that 40 times 9.8 equals 392. That gives us this force here. And that force there, 392, is the force of gravity on the beam. But the beam is not the only thing we have to deal with. The boy also walks out onto the bridge. And the boy weighs 35 kilos. So if we calculate 35 times 9.8, that gives us 343 newtons. So that's another force downwards. And so what we wanted to know is we wanted to know what the force of A and B is. What are the forces, the reactionary forces? If you think about a reactionary force, remember Newton's third law, every force has an equal and opposite reaction. The bridge is going to push down on the banks, A and B, and A and B are going to push up. And what we did is we said, well, therefore, the net force is 0. We said if the net force is 0, then that means that the force of A and the force of B are going to push upwards, so they're going to be positive, whereas 343 and 392 are going downwards. And so we end up with this. We end up with this like quick answer at the end, and that was as far as we got. We ended up with 735 newtons upwards is the force of A and B, but we didn't actually figure out what those individual forces were. That's what we're going to do today. The other thing that we didn't really, the last thing, the very, very last thing I did with you guys, I said, okay, which of these forces is going to be more? And we figured out, well, A is going to be bigger. And the reason that A is going to be bigger than B, which is going to be smaller, is because a lot more mass is on this side of the page. So that means that that's going to be heavier. It's going to push down more. We don't know how much, but we know it's bigger. And that's actually an important skill to be able to do, because then that gives us a way to check our answer. So how do you do a question like this? How can we split this information up? I'm going to show you. We're going to do one key thing. We're actually going to ignore that first force. That might seem counterintuitive, but what we're going to do is we're going to pretend that this is a pivot point. It actually is a pivot point because ultimately if this part of the bridge disappeared, it would pivot around this pivot and fall over. We're going to take that as a pivot point, and we're actually going to look at the individual torques that are going on here. So let's look at the torques. So the net torque is going to be, well, the first torque along is this 343. And that's positive because it's going clockwise. So that is going to be force 1 times radius 1, which we know for this case is 343 times 1 meter. Now, the second force is this guy. The second torque is going to be this guy here, also clockwise. So plus, in this case, 392 times 1.3. The last torque is this force, which is anti-clockwise. So that's going to go up and around in an anti-clockwise direction. And because it's in the opposite direction, we're going to write negative. And we know that that force is, sorry, I should do this, plus F2 times R2 minus F3 times R3, which is going to be minus whatever FB is, we don't know what the force of B is, times, well, this is a 2.6 meter long bridge, so we're going to times it by 2.6. Which means that we're going to get something like 343 plus 392 times 1.3 equals 509.6 minus 2.6 F of B. Or it was like FB, like Facebook. But here's the trick, right? We know, and I'm running out of space here, but you're going to have to make do. We know that the net torque equals 0. How do we know the net torque is equal to 0? Because there's no swinging, there's no rotation, there's no movement. So that means we know 0 equals, I can add these two together at this point, plus 343 equals 852. 852.6 minus 2.6 FB. So we actually now have, we can substitute that 0 in here. And so if we've got these two measurements, I can move FB to the other side, which says that 2.6 FB equals 852.6, which means that the force of B, the force that B pushes up is 852.6 divided by 2.6, which is going to equal 328. And that is our force of FB. Now, if I'm going too quickly, I'm going to say this again. You need to let me know. If there is a part in that whole thing that you don't understand, you need to let me know, because I'm just going to keep going otherwise. You guys have to stop me. Okay, you can message me privately if you don't want everyone to know that you don't understand. But I'm going to go back through what we did here. What we did is we said the net torque, the net torque has to be 0 because the bridge isn't twisting or falling over. To calculate the net torque with respect to this pivot point, we need to look at all of the torques. I can see one torque here, another torque here, and a third torque here. And these torques need to be balanced. Now, someone might say to me, sir, why did you choose that left point? And the answer is, you know what? You could actually repeat this process for that right point and do it from the right going left. And we could actually do that right now to calculate FA. But there's an and we could go, well, we're going to figure out the forces here, but there's an easier way to work out FA. We know that we know that 735 equals FA plus FB. So now we know that 735 equals FA plus 328. So FA is going to equal 735 minus 328, which is going to give us 407. And that's exactly what we thought too. This number is bigger than this number. A must push up more than B. Of course, as that kid starts to walk across the bridge, B will have to start picking up the slack a bit more. But what are the reactionary forces? F of A was the magnitude of the forces. So I don't even need to give a direction, even though I know in this case the direction is up. I can just write F of A is 407 newtons and F of B equals 328 newtons. And that's how to deal with questions with bridges and that sort of thing. There is actually a question that I've set for you guys to do, which is designed to get you guys to practice these kinds of things. But hopefully the other reason that I'm showing you this is that you guys can sort of appreciate these are the kinds of things you need to think about when you build a bridge. You need to think about, well, as objects and people move across that bridge, how is that torque going to be applied to the support structure? How is it going to hold it up? Is there something else that we'll need in order to, support the bridge? If this is a building, like if this is the floor of a building, this could be a stage in a building instead. You could say, is the stage going to be able to support actors walking across it? How are these going to work? And when you do that, you need to take two things into consideration. You need to make sure that the net force is 0, so the stage doesn't fall, but you also need to make sure the net torque is 0, so you know the stage isn't going to swing around or apply more force on one, because you might find that, the riverbank A might not be able to take 407 newtons. So it might just start crumbling, even though the bank B is completely fine. So you might have a limit of 400 newtons. So you want to make sure you use this so you can work out, well, how much force is going to be on each individual side. Even if you're doing something like building a table, how much force is there going to be on one side of the table compared to the other side of the table? Is this going to break the legs of my table if I put a 20-kilogram rock near one corner? What if I put that 20-kilogram block in the middle? How is that going to balance the forces? But yeah, it's all got to do with structures. So that brings us to today's actual sort of analysis, structural design. I wanted to talk to you guys briefly about something that's in the book and something that we should talk about, which is just like, I'm going to skip this for the moment. We're going to talk about cantilevers. Now, a cantilever is a beam. A cantilever is a beam where one end is free to move and extends beyond the support structure. So the classic example of a cantilever is the diving board at a swimming pool. Man, I bet we haven't been to a swimming pool in a long time. But if you look at this, right, the support structure is here, whereas this part of the diving board extends past it. If you actually look here, the center of mass is actually not even underneath any supporting structure. The center of mass is not supported. So how can this design exist? How do we stop this from, falling into the water? And the answer is, yeah, you know what? If there was nothing here, then this would fall into the water. But you have a force here, you have a pivot here, and so that will force it to swing this way. The only way to stop this from falling over is to make sure that you pull downwards on the other side of the structure. And that means you need to put this into tension. You need to pull down. Now, if you actually look at this support structure, there are two beams here. This one has to hold up the plank, so that means this is going to be under compression. What that means is that this whole thing is going to be, this whole side here is going to be squashed down by the weight of the board. Whereas this one's going to be under tension. This is going to be, and so if it's getting squashed, it's going to push up. Whereas this one's under tension, this is going to want to pull away from the board so it can fall down. So that's why we say that in this particular one, this is a cantilever. So the idea is to prevent the rotation, to prevent this from falling over, the beam is pulled downwards on the other end of the beam or structure. That's what this tension force is. Now, vertical structures, like trees or flagpoles, also have this issue. Now, you might not think of them as cantilevers because, but if you look at a flagpole, let's just take a flagpole for example. The problem with the flagpole is that the only way that it's supported is by, the ground. And so therefore, if, there is, at the moment, there is actually, unlike the diving board, there's no force on here pushing it over. But the second you hit a wind, if the wind starts pushing your substance, your thing to the right, then you have to make sure that you have anchored your structure. Vertical structures like trees and flags are also cantilevers. They use friction from the soil to prevent them from rotating. So again, in order for this to rotate, it has to push against this soil. But ultimately, it's the same idea. One end of the structure is free to rotate. So that's why you have to make sure that the other end of the structure cannot rotate at all. In this case, the pivot would be here. And of course, if you did hit it with a strong enough wind, you could probably push against the force of friction in the ground and push the flag over. Same with if you had a big enough person or a big enough object, you could probably push the diving board to break. Now this here is a cantilever building. And I wanted to tell you a quick story I wanted to show you a picture of a cantilever building, and so I chose this cantilever building. This cantilever building, if you ever get is actually a Melbourne uni. So I was a Melbourne University student, and I left the university, I believe, if I can remember it, about 2008, and they were building this No, it was about 2000. It was about 2011 that I left, and about 2011 though. No, it wasn't. That's incorrect too. But whatever. The point is, they were building this building towards the end of when I was at the university, and then I remember I had to go back to drop something off, and I went and I had a look at this building, and oh my god, it was because this is an architecture and design building. It has to look fancy, but I went and I'm just sort of like I knew that the physics was correct, but I stood underneath this massive cantilever, and I was like, a little bit scared. Because look at that. The whole building, this whole section of the building is not directly supported underneath, is cantilevered away. And it's also not just a little like diving board. We're talking about 3 or 4 stories of this building that are just sort of hanging in space. So I was like, shit, like it was insane, but it is massively impressive. It's also one of the things that when you talk about cantilevers, you got to bring up the honest truth is like the only reason why we can build buildings like this and build bridges like this is because we have the technology, the mathematics to be able to do it, and we also have the material research. You wouldn't be able to build this with rocks. Like you wouldn't be able to build this with bricks, but with steel and other structures you can. So this is sort of a testament to how good we are at construction. We can have things hanging over the edge. Now, cantilevers are one thing, and they've actually got the word lever in them. That's why you can actually tell that it's like a lever. You just make sure that one end is fixed down and the other end can, wobble around. So it's like a lever. But we could continue this conversation to, this is a cantilever bridge. You might be like, okay, how is this a cantilever bridge? Well, really briefly, let's look at it. Let me change to a bright color, yellow. We've got this part of the bridge here is clearly supported by these beams. But then this part that extends has absolutely nothing underneath it. So therefore, the only reason, and so therefore this kind of wants to twist this part of the bridge around. The only reason why this doesn't twist the bridge that way is because this is so bonded into the ground that it provides a torque in the opposite direction to balance out that clockwise rotation. We have an anti-clockwise, and of course that bridge is also on the other side, and so that'll do the same thing. But yeah, this is called a cantilever bridge because these middle sections here have no direct support underneath them. And most bridges employ some form of cantilever design, but they also employ other ways to support that middle structure. This one is pretty much just supported by the cantilever anti-action. But you could also have like suspension bridges that have this, but they also have another way to pull them up. Speaking of suspension bridges, this is the last little bit that I want to talk about for today's lesson. As well as their main beams and pillars, many structures have additional ways to strengthen them. Struts will be under compression, and what they do, what a strut does, and this is an example of a strut, is they will compress. And so therefore, if you have a rigid piece of wood or steel or metal, that will provide, as this gets compressed, it's going to push. So if this gets compressed down, then it's going to force the wood up. If this gets compressed in, then this is going to force the wood that way, and that will stop this anti-torque happening here. So sometimes people will put like little struts in furniture to keep them strong. Of course, if you've ever seen a bridge before, you know that there is a bunch of struts in the bridge. Yeah, that's what the purpose of a strut is. Sort of the opposite of a strut, coming from a vertical direction, is something called, I guess, a tie. A tie is like the opposite. A tie is under tension, and this is when we talked about suspension bridges. This is how a suspension bridge works. They can be flexible or they can be rigid, so you can make a tie out of wood or steel or whatever. But how a tie works is, again, yeah, this person's going to apply a torque that goes clockwise. The tie applies an anti-clockwise torque by pulling when it is pulled downwards, and as a react, I'll do this in different color. It's pulled downwards by what's that force called? It's pulled downwards by tension. So in order to battle that tension, the reactionary force is that the wood gets pulled upwards, and so therefore that balances out this torque, and so therefore you can sit on it. If you think about swings, if you think about picture frames and so on and so forth. So that's how you would do, that's what a strut and a tie is. And that just links back to this idea of constructing buildings. All right, so now, ladies and gents, I'm actually going to skip this idea today. I'm actually going to come back to this idea, I think, Thursday. And it'll just be a little thing that I'll talk to you guys about how to solve questions with torque with regard to that. But I've talked to you guys for a fair while now.